Okay, so we're introducing this new concept of integration, which is supposed to be like the twin, whatever, to differentiation. And so today we're mainly concerned with some notation about how we write down what an integral is. So already you should have a sense of what an integration approximation is. It's adding up all these rectangles. Just like differentiation is rise over run, and that if you're ever really stuck on a differentiation problem, you can always do a little interval and you do a little rise over a little run, and that'll tell you the derivative. That'll give you a good approximation of the derivative. Same thing with the integral. If you ever stuck on an integral problem, then you can always just like add up lots of little rectangles, and that'll tell you what the derivative is. Okay, so last time we talked about, okay, we have a function like this. And so one thing we can do is say we want to find the change between 2 points A and B. Or another way, we want to find the area underneath this curve here. Then we just make a grid of points that will then give us bases of rectangles. We then take the heights of the rectangle. We just got to choose some point on the curve to be the height of the rectangle. So we can do a left-hand sum. We can do this kind of stuff. Really tries your patience after a while. Okay, and then we could add up all those rectangles, or we could do right-hand sums. So let me go from this direction using right-hand sums like this. And I introduce some notation. So left-hand sum, okay, is equal to like the summation. So that sigma tells us that it's a sum, and so this is maybe x0, x1, x2, all the way to xn, because we've got n rectangles. And you know that if you have n, if you take a segment and you cut it at n plus 1 points, then you get n intervals. So it's a little bit annoying because there's one more n point than there are intervals, right? Because there's n left points, n right points, but there's n plus 1 points altogether. But anyway, the left-hand sum is where you n minus 1. So we count n rectangles this way. We start from 0 and end at n minus 1. That's the height of our rectangle. And that's the base of our rectangle. So here, delta x is whatever interval we're interested in, divided by n, the number of rectangles that we use. Okay, and the right-hand sum is, well, we do n this way. We go from 1 to n. Again, fxi delta x. And from a numerical point of view, best estimate is just to take the average of the two. That tends to give you the best answer, but that's just a numerical technicality. Okay, these still give you estimates, and the nice thing is if we let n go to infinity, i.e. we're cutting it up into finer and finer rectangles, that's the same thing as letting delta x go to 0, right? As n goes to infinity, the rectangles become skinnier and skinnier and skinnier. Both of these things will go to the same answer. Just like, remember when we did the derivative, remember we did a little interval, and we could have the point we're interested at the left-hand point, we could have it at the right-hand point. The best was to have it in the middle, but it didn't matter. If you took it to 0, you would still get the same answer. Just putting it in the middle just got you the answer quicker. The same thing here. This will go to a better answer quicker, but they all go to the same answer. And now here's the key point of today's lecture. What do we call that answer? We do this integral. This is an integral sign. It's kind of like elongated S. S for sum, just like sigma is for sum. At the top and the bottom, we put what the endpoints of the interval are. We put the function in here, and then we write dx. And so these are the limits of these things here. And so you should just see it. When you see this sum here, you can see what we're talking about, right? Here is the f of x, goes there. Here's the delta x. Well, that goes to dx in the limit, just like delta y over delta x goes to dy dx. The same thing. And then the sigma gets turned into that. Okay? And this thing here is called a definite integral. Okay? It's an integral because we're doing integration, which is this reverse process from differentiation. It's called definite because we have some interval that we're doing it over. Later on, we'll talk about an indefinite integral. And that's one that doesn't have these bounds, but it means kind of something else. But we won't worry about that for the time being. Just at the moment, we've got this idea of the definite integral. Okay, so let's have a look at a problem. Okay, so here is an Excel file that I made to do the computation. So remember, I made Excel files before for differentiation, just so that it does the simple arithmetic of division. Here, we've got more complicated math, but it's still just arithmetic, right? It's just multiplication and addition. But the trouble is, like, to get a really good limit, you have to do lots and lots of additions. And so that's just kind of too tedious to do by hand. Like in an exam, I wouldn't ask you to do more than kind of like 5 rectangles. That would be kind of the upper limit for in a time restricted environment. And for a homework, maybe 20 by hand would be a lot. That would be tedious. But with Excel, we can just kind of just do it. So let's have a look here. So you can see here, what have I done? Here I've got the bounds of my integral, so I'm going from 0 to 20. And here's n, I've got 20 rectangles from 0 to 20, so that means my delta x is 1. Right? It's just this minus this is the length, divided by n, that gives me the widths of my rectangles. Okay, so here is my grid of points, it goes from 0 to 20, and here is my function in this column here, and if I click on it, I see that the function is 570 times 1.037 to the x. Okay, so this is a population problem. Okay, because it's something to do with exponential growth. So let's just say we're doing a population. So what we're talking about maybe is we're talking about maybe a town. Maybe this is thousands of people. Okay, so we've got a city, we've got 570,000 people in it, and we're told that the city grows at 3.7% per year. Okay, and so here, this is what we start with, 570,000, next year 591,000, etc., growing by 3.7% per year. Here is, okay, that's a different problem. No. Now this is the rate of change is 570. Okay. Now, what was my problem? Okay, I don't like this problem. I'm going to change it. I'm allowed to do that. So remember in the class last week, class yesterday, I talked about bacteria growing at a rate of what was it? It was like 3 plus 0.1 t squared. So I'm going to change it to that. 3 plus 0.1 times A2 squared. Okay. And then I'm going to copy and paste. Okay. So this is the rate of growth of our bacterial population, and so since it's a rate of change, when I differentiate it, that gives me the total accumulation. So this tells me how much extra bacteria were produced in that 20 hours. Okay, so here is our function, and so we can go ahead and take the integral. So here I did the left-hand sum. Here I did the right-hand sum. So what we do here is, you see what happens is the width of the rectangle is 1. So we start off with 3 plus 3 plus 1 plus 3 plus 4 plus 3 plus 9, etc. This running sum gives me the left-hand sum. This running sum gives me the right-hand sum, right? And so my answer then would be the average of the two. So let's write down this information. Left-hand sum, right-hand sum. And so if delta x equals 1, the left-hand sum was 307, the right-hand sum was 347. So my answer would be maybe 327. Okay, so maybe next I want to do a better approximation. So the way to do that would be to, instead of say doing 20 rectangles, I would do 200. Okay, and then I see, oh, the trouble is it now only goes to 2. So I'm going to have to go ahead and complete it to 20. So it'll go to like, go to 200 maybe. Ah, there we go. And then I don't need this guy because I'm doing the left-hand sum. Okay. So the left-hand sum goes from 0 to 19.9 now. And so that's 324.67. 2/3. This is 328 and 2/3. So my answer here would be 326 and 2/3. The average there. So, how confident are we in our answers now? Does this look good? Yeah, it looks like we've got really nice convergence, doesn't it? So we see that this answer here is going to be pretty good. It hardly changed at all from there. So this is, I would put, this would be my answer, and I'd be very confident of it because this guy is converging to it, but these guys are also converging to it. So we've got like everything here seems to be converging on that number. So this answer here is a pretty good answer. Okay. Now the only trouble is we had to do a lot of arithmetic to get there. So that's why we have the Excel file. And so that's why later on we're going to be learning some formulas so that we can do it. Just like we did formulas for derivatives, we're going to find out we're going to have formulas for intervals. Okay. But at the moment, we've got that Excel file. And so if you use that, you can use that to find pretty accurate answers. Okay. So let's kind of do another one. Let's do another. So how would I state the problem? So I'd state the problem would be something like find integral, let's say between 0, let's say between 1 and 3 of e to the minus x squared dx. So let's go and do that. Okay, so I have to change my bounds. My a now becomes 1. My b now becomes 3. And let's see, we start off with, I don't know, 10 n. Okay. Okay, so our interval is 2. We're going to do 10 rectangles. So that means the width of our rectangles is 0.2. Okay, so again, we'll do left-hand sum, right-hand sum, average, and we'll have n being 10. So in this column here, we can put either n or delta x. It's got to be something which signifies what we're doing. like either the number of rectangles or the width of the rectangles. Okay, so let's find 3. So 3 is here. Okay, so the left-hand sum is going to be from 0 to 2.8. So it's going to be that number there, 6.788. The right-hand sum goes from 0.2 to 3. So it's going to be, which one is it? It's going to be this one, 6.948. Okay, that's okay. Their numbers are pretty close. So we'd see that's going to be pretty good. And so we would just take the average of that, which would be 6. What's that? Between 7.8 and 9.4 is 868, I believe. Okay, so now we would do a better n. So maybe we do n equal 100. So notice there's a bit of, you don't always have to do the same thing, but you kind of have to do something similar. You start off with some number and then you do a bigger number, and usually you try and go up by something geometric. So you might do 10, 100, 1,000, or 2, 4, 8, 16, or something like this. Okay, 100. So we're still looking for 3. So we go ahead and find 3. If I put my glasses on, I'm sure I can find it. Okay, here's 3 here. And so now the left-hand sum goes from 0 to 2.98. And so we've got 6.85868. That looks like a pretty good number to me. The right-hand sum goes from 0.02 to 3, and it's 87468. And again, that looks pretty good, right? Because now they're pretty close together, and we look at the average, and it's going to be 6. I'm going to do this on that. Average of what things is it? It's C 101 and D 102. Okay, we see the right things are highlighted, and it's 6.8. 3 6s. How do we feel about this answer? We feel good about the answer, right? Because again, we're seeing stabilization. We did a big improvement. We went from 10 to 100. That's a big improvement, right? And we saw a little change. So that's a sign that this is a good answer. And again, we see that the average is going there, this is going there, this is going there. Okay, so that's how we go about actually solving things numerically. And this is still how a lot of things are done. Because it turns in the real world, often you don't have formulas. You just have data, right? And so people all the time numerically integrate. They do exactly this kind of thing to find out information. So sometimes this is actually the quickest way to find an answer is to do this, because they all do it on a computer, and the computer can do, not just 100, but it can do millions in an instant, right? And so using that, you can get really good answers without having to do the kind of stuff that we're going to learn about later. But that's as it is. Okay. So that file there is integral. It's on Blackboard. And so anytime that you need to numerically integrate, you can use that. As well, on your calculators, on graphing calculators, quite often there's an integration thing. So if you look up your little guide to your HP graphing calculator, there's a feature there that will actually do integrals for you. So there's lots of ways you can go about finding these answers. Okay, so that is that's how we do numerically when we've got a formula. And of course, let's just quickly do another example, another numerical example. Let's do integral between 20 and 30 of f of x dx. And now we just have a table for f. So here's x, 20, 22, 6, 30, 5, 7, 11, 18, 45. Okay, so this is exactly the kind of problem that we did yesterday, but now I'm just wording the problem as define this to ask you to do an integral. So again, you do a left-hand sum and a right-hand sum. So what are the width of my rectangles here? The width of it's going to be an actual number. So what are the width of the rectangles that we're going to use with this data? Which number are we going to multiply things by? 2, yeah. The 2 is between here. So our interval is 30 to 20. We're going to use 5 rectangles. So the width of our rectangles is going to be 2. So it's going to be 2 for both of them. What are the heights of our rectangles? Well, the heights for the left-hand sum are going to be the left-hand endpoints. And for the right-hand sum, it's going to be the right-hand endpoints. So it's going to be 7 plus 11 plus 18 plus 29. Okay. So this is, as I said on a test, this would be kind of like your most complicated computation to do, like around 5 rectangles. And so you do 12, 23, 41, 70, 140. 18, 36, 56, 65, 110, 220. And we just add these two together, 360 divided by 2, 180. So that would be our best guess for what that integral is. Now, the only problem with a numerical examples like this is we can't get a better answer because we don't have, to get a better answer, we need more data. We need to know what's happening at 21, 23, 25, 27, etc. That's that. How about a numerical problem. No, numerical. I've given you numerical. I've given you a formula. Graphical problem. Okay. Let's see if I can make this work. You see? No. Now I get the document camera. I haven't. Oh, I know what I do that, don't I? Now I get the document camera on. Getting a terrible picture there. Let's see if I can get that any better. Oh, that looks better. Okay. Okay. Sorry, people at home. This is the best I can do. Okay. Here's an example of a graphical problem. Again, you're told to find something, an integral. Okay, and so we know it's going to be from 0 to 6, and it's going to be the area underneath that curve. Now, the things that you could use to guide you are these squares that are here, these rectangles, right? So each rectangle is a 1 by 5 rectangle. So we just try and add up, count them up, and that's going to be our estimate for the integral. So I actually started doing this. 1, 2, 3, 4, 5, 6, 7. So there's 7 whole rectangles there. Each rectangle is 5. We've got 7 whole ones. And then you start going through and you start seeing, well, can we get things set? Like here, I said, well, this plus this maybe looks like a whole square. So let's call that 8. This and this together look like a square. Actually, it looks a little bit more than a square. So let's call that 9. Whatever's left over, we can put over here. We can say that's 10. So approximately there's 10 squares. So 50 is our answer. Okay. So again, this is a nice one where it's good to have like a ruler to do it and just be careful. But yeah, that's as good as you get. You start looking at rectangles and triangles, and you try and piece them together to estimate the area.
I have a question.
So that's the 3 basic kinds of problems you can get, right? A formula, a table, and a graph. Okay. So this is basically, this slide here kind of gives the basic concept that we dealt with today. So we're going to be talking about a function which is continuous on some interval. Right, we really don't want to worry about, functions that sort of higgledy-piggledy all over the place. We're just talking about continuous functions, kind of like this, where it kind of makes sense to cut things up into rectangles and triangles, right? And so we have this idea of a definite integral as being the limit of this thing. This kind of sum here is known as a Riemann sum. Named after the 19th century German mathematician who came up with this. Just like we had Leibniz and Newton in the 17th or 18th century. Now we have this guy in the 19th century. And we think about these as a limit of these sums. Okay? Now it only makes sense if these limits are the same thing. Right? So if you had some kind of weird function, and it would have to be non-continuous, just like, remember when I showed you that snowflake function, which was kind of like weird and didn't have a derivative. So there does exist functions where you can't integrate them. But then that's not going to come up in this course, and they're kind of harder to define. Okay, so the limit of a Riemann sum is going to be the integral. Okay, so this is called a definite integral. This is called the integrand. It's what you're integrating. And these numbers here, A and B, are called the limits of integration. So we're integrating between A and B. So that's your basic vocabulary right there. Okay. So look at this example here. We have some function g of x, and we use some rectangles to approximate that integral. Okay. This a left-hand sum or a right-hand sum?
Right.
It's a right-hand sum, right? Because we're taking the right-hand point to be the height of the rectangle. This is, what kind of sum is this? Left hand, exactly, because we're using the left hand point. Okay, this is just a vocab test, right? Okay, is this giving an overestimate or an underestimate? Overestimate, right? Because the rectangles lie above the function. Underestimate, because the rectangles lie below. Okay, great. What n am I using? I think you're putting them both together. Just take one at a time. What's n here? How many rectangles are there?
Oh,
3, right? N is 3 in both cases. And finally, what is delta x? What's the width of the rectangles? 2, exactly. It's 6 divided by 3. Okay, so that's all the basic terms right there. So understand this. This is what we're interested in. Okay. So in this one here, this is just a graphical problem. You just have to do it by eye. Okay. Here's an integral between 0 and 9 of f of t. Which one of those numbers do you think is going to give you the best estimate? People at home can play too.
Either 13 or 18.
Putting all the pressure on the girls here. I don't know why. All the guys are at home.
Can you hear?
Eric's going to say something? Oh, sorry, Eric. I don't think I got the sound on. So
It would.
what do you think is the best guess? So everyone think. Could the answer be 30? Right, because this is 9, this is 3. How big is that rectangle here? Sorry? Yeah. 27, right? So this area is 27. So could this area possibly be 30? No. Okay, so if this area is 27, what's your best guess for this area? Is it going to be, it's going to be less than 27? Is it going to be bigger than half of 27? Because half of 27 is going to be this triangle, right? So it's going to be bigger than half of 27. So looking at that, what would your guess be as the answer be?
18.
Excellent. Yep. Right. So you can fit this triangle here, which is going to be 13.5. So it's bigger than 13.5. So that gets rid of A, C, and E. And it's inside the rectangle of 27. So that eliminates 30. 18 looks like around right. Okay. Hang on. I'm going to see if I can fix the sound problem. Oh, here was the problem. I got the. Oops. Okay, the people at home can now play. Right. What about this one? Okay, we've got an increasing function that goes from 10 to 18. So it's looking like this. Starts at 10 and go up to 18 at 5. So it starts here and ends here. Somehow it goes from here to here. So we're looking at that integral between 0 and 5. Again, which one of those do you think is going to be the best possible estimate? Yeah, you've got it. Okay, right, because the smallest is going to be 10, right? So it's going to lie over this rectangle, which is of area 50. So the answer's got to be greater than 50. So that eliminates A, D, and E. Up here is 18. So it's going to lie within this rectangle, which is an area of 90. So the answer has to lie between 50 and 90. And B is the only one that can work. Okay, I think you've got that over. Okay, I think we've got time for this one. Okay, so here we're given as a graph. Okay, so this is a weird kind of question. So try and think of an interval on which the left-hand sum is going to be an underestimate. Now, let's think about this a little bit. When is the left-hand sum going to underestimate a function? So we want the left-hand points. So if we have something like this, right? This is the kind of situation where the left-hand sum is going to lead to an underestimate, right? Because the left-hand point is kind of like the lowest value of the function on the interval. So what kind of function is this? What do we call a function where the left-hand endpoint is the lowest value? As distinct from this function, where now the right-hand endpoints is an underestimate. What's the difference between these two functions? Yep. So if a function is increasing, the left-hand sum gives an underestimate, and the right-hand sum gives an overestimate. Whereas if it's decreasing, it's the other way around. This is kind of why it's the best to average the left-hand sum and the right-hand sum, because you're kind of balancing between the increasing and the decreasing. Okay, so on what interval would the left-hand sum give an underestimate? Well, that's going to be on an interval where the function is increasing. So what's an interval here in which the function is increasing? Yeah. Right. And where will it be an overestimate, or where is it decreasing? Yeah. Yeah, so 1 to 3 would give you an underestimate. Oh. Okay. So we're doing y equals x squared. And we're doing the interval 0 to 4. And we want to have the right-hand sum for 8. So which one of those is going to be the right answer? Why is this wrong? Remember, we're adding rectangles. Why isn't this a rectangle?
It's a square.
It's a square, right? Because we're doing the function square, right? So these are heights. What's the width of the rectangle if we've got 8 equal subdivisions over 0 to 4? What's our delta x? 0.5, right? So exactly these three things do give areas. Okay. So these things are giving us bases, and now we want to do heights. Okay, which one of these three then gives us the correct height for a right-hand sum? Well, it can't be B, right? Because it's 0.5, 1, 1.5. That is, you're not squaring it. So it's not the heights of the rectangle. So it has to be one of C or D. Okay. One is a right-hand sum and the other is a left-hand sum. Which is the right-hand sum? C. Yeah. 0.5 squared, right? So yes. So it's giving it right here. Okay, that's all we've got time for. So tomorrow we have the test, remember? So see you then. 5 people at home. Ooh.